Some of you have been on my first talk, not? Only two persons, yes. So this is motivation for considering isometry is that, for example, most very important isometry is Lorenz group. Set of all isometries is a group of isometries. And where I have isometry, I should write here group. And what this is process. Every isometry is process, and this process is conserving metric. Conserving metric. This, you know, maybe mathematician. Now, maybe you know that is there's a synonym means that there are different names for the same concept, right? Synonym. It's okay? But synonym, and this is homonym is correct. The same name, but has many different meanings. Many different meanings. Probably, do you know some example of homonyms? Nobody? What? What? Change. What are two meanings? Something changing or money? Oh yes. Perfect example. And this is very important concept, isometry. This was presented by Jerzy Kocik on yesterday on class. Was 2 minutes he taught about isometry, but you use name symplectic group because if this tensor, because this is tensor, but this is tensor. It is not allowed to use this word because Jurek told me that not yet introduced a tensor to his class. But this is very simple concept, tensor. It's nothing difficult, but we must use this tensor. So if this tensor is symmetric, we have orthogonal group. So this group is, in case of G, because this is morphism, and morphism acting on dual space, I denoting this way. Jurek denoting by transposition because he has matrix. I have no matrix. No matrix, no basis. No basis, no matrix, because vector do not possess components, only basis is associating to vector. Vector do not know what components has. Also, operation do not have matrix, you need basis. So if no basis, so if this is symmetric, this isometric group is called orthogonal group. But if this is skew symmetric, Jurek denotes this by epsilon on his lecture yesterday. Then you have a symplectic group for this tensor. Okay, let's write this. I don't like notation of Jurek, but everybody has his own notation. Is personal love. Okay, and okay. So motivation is that among many different isometries is isometry is Lorenz group is the foundation of the special relativity, and from this isometry comes many strange consequences of relativity theory. So I do not have infinite time, but I like very much this notation of Professor Kaufmann, this braids this language. I'm using language of operats. Maybe this is not necessary. You don't like to sit down in center? No? It's okay? It was in terms of the graphs. Graphs as nodes and arrows here. Well, what is? No, graph is nodes and edges. Okay, because in Spanish aristas. I know I'm teaching in Mexico City, and me Spanish and English are. Yes. Okay. So was Hurewicz, Professor Hurewicz Witold from Poland, as Hurewicz, in his lectures in MIT, he introduced for the first time denoted process in terms of the arrow. So if you have input here, domain of function, then he denote function as, and here is range, in range. So what normally we put x here, and he use arrow, and here is value in range is this notation. This notation, who is using this notation? Jurek is using? No.
Every other day, yeah. On even days.
Okay. So you know, so this is graph, because this is a node. This is age, yes, age, and this is another node. But Professor Kaufman knew better history of operat. This is language of operat. Operat is not operation. It's just MacLean was using different names. There are many different names for this graphical calculus. But okay, I remember that Joyal Street was first who introduced it from Australia, from Melbourne. Joyal and is correct or by A? Street and 87. They paper that they introduced the Lu.
I thought it was earlier.
Yes, and then that he changed this notation. This is probably independently was invented also by Jerzy, no? But you know, we must cite who published this independently. But okay, I don't know how people, for example, you are writing from the left to the right, but I prefer, as in China on Japanese language, from top to the bottom. They said, you also write this diagram from, this is input, right?
Yeah.
This braid diagram from top to the, here is output, yes? In this I'm also using only this. So my diagrams, my papers, you must read from the top to the bottom. Not from, freedom of notation, at least freedom of notation, because you cannot speaking free. No. Okay, so he Joyal Street that the input is line. Input is age. Input age and output is also age, and process is not. So this is input. This is process, and this is output. Maybe MacLean, maybe as I don't know who really invented this idea to write processes, but this is like in electrical engineering and also in computer science, that node is most important process is here. So therefore, this function we denote in this way. This is f. And here is input. You can put here what you want. If you put here x, then you're getting here a value fx. So this value is associated to this line. Of course, Jurek is using Jurek is using box. Here is f, and here is, and then he is using arrows, and for example, therefore his diagrams one can read as you want. You can rotate, right? But I do not use arrows. I do not use arrows. Therefore, I have a convention that must be read from the top to the bottom. Okay. It's almost everything. Not. Okay. So we remove this. So situation is such that if you have a process, you could have many inputs. Here is the objects. This is category. Category we have objects. Objects are input and output, right? So this what was really, so objects are really natural numbers. Here is a little problem because not everybody accepts 0 as natural number. But this is difference between different people. Okay. You accepting 0 as natural or?
Very natural.
Natural? Okay. So, so you have, for example, here input is 3. For example, you can have maybe 4 output. So this is morphism. Every morphism has information. What is domain of morphism and what is range. Every function, every operator, without specify domain and range, it has no meaning. So therefore, all this domain and meanings are graphically presented in this way. So this is morphism, and against me? No. But because I can write here this 3, 4. Okay, we have many such. So what this tensor is? This tensor has this tensor G is morphism because Jurek denotes this by this. By such notation, do not have information what really domain and range is. So I'm denoting this by this letter V. So here is input. Input is 2. You must this is a function that apply to pair of vectors, scalar. Is okay? So maybe you prefer you use notation of Jurek, but here output is 0, scalar. So you put one vector, another vector, you are getting scalar. This notation. This is graphical notation as using, and this is in category to 0. Okay, now problem is that we must always consider category with duality, that every object has a dual object, a two-sided dual object. Which one? So so I don't know what to use, maybe two colors that with two operations. I mean, if you have space and dual space, there is an operation evaluation that associate to pair of vector and covector scalar. Yes, there are two such evaluations. Okay, let's write here in this way. This is okay? No. Better some another color. So for this is vector space, and here another color is dual space of covectors. This is really, I'm not enthusiastic to my lecture because take a lot of time this notation. Maybe we do not need this so much. Okay, so this is evaluation, right evaluation, and there is also another letter here, and here this is evaluation from the left. So if you have, okay, maybe I can write here vector space dual. If here covector comes and here comes vector, this process evaluation associating to pair scalar. And here is just opposite because this is a tensor product of two vector spaces. They are totally different tensor products. Tensor product does not commute. They are two different. So from the left, from the right, you can get different story. So these are evaluations. So evaluations are maps from, okay, tensor 1 to 0 and opposite. And there is a very important co-evaluation. All this is in the paper of Plaza and, I don't remember. No. This is 1980. Plaza, not remember? From Australia. This evaluation co-evaluation is they introduced it in this year, and they introduced the name closed up category. If possess dual objects with evaluations, because if you have vector covector, you do not need to evaluate. Still could be tensor, one tensor. But this evaluation is exactly the trace of such tensor 1, for example. But you do not need to apply this. So this is analogy of this. And another, I forget names of authors. Another is that you have co-evaluation. This is processes from okay, there are two, left and right, co-evaluation, okay, left, and co-evaluation right. So if those are just like primitive letters in our alphabet. For example, what Professor Kaufman wrote, he has also this letter. This is braid, satisfy braid equation, right? But from this he built not. But I need for this 3 letters. I need this letter because this letter is from 2 to 2. Could be primitive, could be built from other letters like language. Okay.
Like in the bracket version, it expands into evaluation and co-evaluation. And
Okay. But we can also, if I have this letter, which is from 0 to 2,
yes.
if I have this letter from 2 to 0, I can join. If I have this letter from 2 to 0, and I have this letter from 2 to 0, and join, this is your knot, okay? But this knot is word in 1, 2, 3, 4, 5 letters. In 5 letters. So this language.
These categories generalize the break
Yes.
category by the addition of the duality.
Yes, by additional. Yeah, I can choose evaluation, coevaluation. I can choose this scalar product. Depends on this quasi-triangular structure. Depends what you want. So you have many primitive letters, your alphabet, and from alphabet you construct all processes. If this is not enough, you build another alphabet, another processes, and this is, and then you can introduce axioms, and quotient of this language for axiom is exactly operand. And this is, well, I remove operand. Okay. So it is short introduction to operand. Operand is language when every letter is graph. Every letter is process, primitive process, with specified domain and range. And then you can compose processes as you want. For example, if I have this process and I have this process, I can join. Okay, so this is word of 2 letters because one letter is this one. So they have domain 0, range 2. Another process is domain 2, range 0. But if you composing, you get something from domain 1 and range 1. But you can, from 2 letters, you can build many different things. Okay, this knot is 0 to 0 because you have 0 to 0, and we postulating that this must be ring. This is a ring on which all the objects live. Element of the ring. For example, this is if you postulate natural number, this is exactly the dimension of our vector space, for example. So we don't know if this is language of is sufficient of this introduction to operand. So if you postulate some letters, then you can join, compose any letter with any letter in many ways. Normally, if you have 2 operations, looks like that you can only, but you can compose in only one way. If you have one function, second function, there's this. But here, the letters, you can compose from 2 letters many different processes because you can join even if you put concatenation. This concatenation, for example, what Professor Kaufmann wrote, this letter, no, is the same as, of course, this and this. And this is from 2 to 2. This is totally another composition, concatenation, which they commute 2 processes. But this is from 0 to 0, from the same 2 letters. This is 1 to 1, from the same 2 letters of alphabet. You can compose in many different ways. So you have much more flexibility. This language is much more flexible. Okay, so now we have only a few minutes to party. So this tensor G is tensor that has 2 input, 0 output, and inverse of this tensor is has okay, I can write maybe in this way, is just this process. But if you compose this with this, yes, or you can compose this with this, and you can put this upstairs or downstairs as you want, and this must be exactly identity, because composition inverse with tensor must give the identity. This is zero move of Rademeister, zero move in book of Professor Kaufmann. So this is definition of inverse of this metric, or symmetric or skew symmetric. Is okay? So now element of this isometric group must be, of course, I do not finish this homonym. I do not explain. Because isometry has 3 meanings, as I know. You can, 3 different meanings. One, that you have distance, that you have no metric tensor. You have distance on manifold, distance between 2 points. And you make transformation of manifolds conserving distance. This is called isometry. But Greg, this is totally another concept. The same name, totally different concept than preserving tensor that have associate to pair of vectors scalar. This is another concept. Another concept is the preserving is a killing symmetry. Symmetry, I mean that you have a diffeomorphism of manifold such that tensor, metric tensor is invariant. So this killing symmetry is acting on points of manifold, on functions, and then they are defined by means of the Lie derivative of G0. This is Pietroff classification of metric tensor in terms of symmetry of metric tensor, diffeomorphism. Yes, and third is as this G isometry algebraic. Algebraic because this group of isometries do not act on manifold, do not touch points, do not act on functions, but act only on tensor, on vectors, rotating vectors, and transforming all tensors, and one tensor is preserving as invariant. So I denote this by L, and this is this is isometry, one element of isometric group. Now I'm going to define isometry, algebraic isometry. Definition. Definition is such that if you have this metric tensor that has 2 vectors as input and scalar as output, so if you put here this L, we are composing. So here from 2 to 0. So definition that this must be the same. This is usual definition of to be isometric, preserving scalar products. That if you put here 2 vectors and here 2 vectors, but then you rotate vector and rotate this vector, you applying scalar, result is the same. So this is preservation of this tensor, not scalar tensor. But if we apply to both sides. I have this, okay. Co-evaluation, if we apply here, yes. Okay, okay. So you see, this is process that vector as input is changing to covector, So if you put this in the box like Jerzy like, I do not like, but he like. Okay, so if you put here, so this is new process built from two processes, because here is okay, here is G, and here is co-evaluation. Co-evaluation. From two letters you build new letter, 1 to 1, and this, okay, this letter people do not from, this is map from 2 to 0, but this one is map from 1 to covector. So you have, if you have a dual object and you have boring. This is a lecture for students, so professor should not. Okay, so there are two different points to interpretation what metric is. One interpretation that this is associating to pair of vectors scalar. Another, this is map from vectors to covectors, from particles to waves, because covector is a mass primitive concept for wave, for differential forms, from vector fields to differential forms. And here we have the following situation, that whenever we have, okay, this is exactly what Jerzy presented. This is co-evaluation. Here is endomorphism of vector space, but you know, on these diagrams, there's a corals you can move as you want. So like in the diagram by Professor Kaufman, you can topologically move crossing, but not destroying not. Yes, this is something that if you move, okay, here is co-evaluation, here is L, and you can move this coral to another side, and this is what I call, what you call transpose of mapping L, transpose. And this is no adjoint, because this is action on dual space, but you need co-evaluation. You do not have scalar product, you do not have Hermitian structure, you do not have brackets. No. This is totally, this is dual. Every action, because you see that if you put here, because you have one process, second process is identity, and output is the same. You must all this is axiom. This is axiom. All axiom is that for the same input, you must have the same output. So this is postulating. It's not going to be proved. Not for every process acting on vector space, there is a process acting on waves that they give exactly the same result. Yes, the same result. Therefore, one can move this here as okay, we have L here, and now you see that here is co-evaluation, here is G. So this side, many people do not understand the three meanings, because they mixed on many conferences I meet that they mix the concept of meaning of the isometry. But So if you put in box this, okay, so what you're getting from this side, you're getting that you have, okay, so this is our process. Here is this G from 1 to 1, and here is going to wave, particle-wave duality, from particles to wave, but here is this L. So finally, we can write a definition of this process. Okay. This is exactly what Jurek wrote yesterday on another blackboard. This must be exactly this. I like that you see that this is from the word of the vector fields to differential forms. And this is composing with co-evaluation from what we have here. This is this, right? And if you go back with evaluation, you're getting this. So we have evaluation, co-evaluation. Evaluation, if you compose with evaluation, you're coming back to this condition. So this condition and this condition are equivalent. Evaluation, co-evaluation are like opposite action. Interesting or no? I don't know. Jurek said that we need always in pictures in mathematical papers. Yes, maybe I can show this my pictures if I have here some. No. Aquí. You have from my paper, but give me back, okay? You can see how this axiom looks like, because this is only copy that I have. But if somebody like, we can make a copy. And
yeah. So we have another class coming in at 5. So they're going to be coming in now, and so we should maybe have some questions now.
Okay.
Okay. Are there any questions?
No question. Okay, thank you very much. But if somebody is interested in this, let's say, apparent language.
Was there a question here?
Well, is this how you're getting the lack of associativity in the Lorenz group you're representing? You have 2 or 3 possible inputs, and you're getting one output. There's 2 different ways to do it. And is that how you bring it up?
No. You know, we know that G is given. So if you change G to Schwarzschild metric or some another symplectic form deformed, or you can take every tensor has isometry group, but they different subgroup of GL, So my achievement is that I solve this equation. For the given G, I found most general L such that this is identity. And with this most general L, I then compose 2 such isometries, and I deduce this composition of velocities, which I presented previous time. Very bad formula.
So in the sense, the Lorenz group is really one of these L.
Yes. This is definition of the Lorenz group. For arbitrary metric, for arbitrary curvature, for arbitrary, also definition of symplectic group. Different symplectic structures on manifolds, they give totally different symplectic groups. No, Jerzy claims that they must be isomorphic, but you know, manifold with curvature no zero, in manifold curvature zero, they are still something different, and I prefer yes. Oh, yes. Mm-hmm.
How does the categorical formalism help in handling the compositions of relative velocities in different vector directions?
No, this isometric group gives only one formula for composition. This formula is contradictory. It has many drawbacks. One drawback that is non-associative. It is not in reality, we do not have that dog has two different velocities. The another drawback is inverse, that if inverse formula has only one solution for inverse, reciprocal. The minus velocity is the only solution for inverse. But if you, for individual, but if you add two velocities and you apply this inverse, it's not inverse. It's mystery, but this was the first observed 30 years after Einstein passed away. And you know, and this information you can never find in no one books of relativity, that addition of velocities have such three drawbacks. They are not mystery, like, no, they are not beautiful properties of relativity theory, as Ungar in his book, he wrote that this is beautiful. But this is mathematical contradiction. You assume one, and from assumption you conclude contradictory the assumption. So therefore, this is really a problem for mathematicians, not for physicists. A problem for good mathematician student to think about why such stupidity comes into the play. Jurek said that this is subject for physicists. Not. This is very difficult problem for mathematician. Why this illogical situation comes? That we assume, no, there are many other problems comes here that I have no time to finish. That if we calculate, if we fix two reference system and like to calculate all possible velocities between reference system, we get infinite many from this assumption. There is no one velocity of bus respect to the street. There are infinite many velocities between bus and street if bus is boost of the street with isometry. So isometry, how comes isometry in science, in physics? Because this is symmetry of massless Maxwell equations. Maxwell equation you can express in terms of the metric tensor, and symmetry of metric tensor is symmetry of Maxwell equation. Symmetry of differential equation, what means? That if you, with symmetry, if you change solution of differential equation, you get again solution. So symmetry of differential equation, domain of symmetry of differential equation are solutions of differential equation, and solutions are permuted. And you never, from symmetry, you can never go from solution to something that is not solution. This is Lorenz group. This is conformal group, never change symmetry of massless Maxwell equation. But it was postulated, decided, believed dogmatically that this group is good group to remove, that if symmetry of under the group is equivalent to be independent on reference system. Lorenz symmetry is believed to be equivalent to independence on reference system, and it's not the case. It's not the case. And to be independent on reference system is the only structure, mathematical algebraic structure that is good is groupoid. Groupoid that is not group. Okay, thank you very much. Thank you.